Yeah, good evening, everyone. So today we will look into the deep main concepts. So before that, if you have any doubts, maybe you can start with that.
Sir, I've added the Trackio, but it will not showing. It will showing not added the Trackio.
Oh, okay, so this is NPP, right? So you can fill the discrepancy form mentioning that one.
Okay, sir.
Yeah.
Sir, what are we going to
Expected date for NPP2?
Uh, it will be around on the next week. This time we'll be starting around in the midweek rather than Friday. So plan is to start it in Wednesday, 12th December. We'll also send out an announcement regarding the date.
Sir, the NPP is next to next week,
Yes,
like
yes, 12th,
after
12th
December
December.
7th.
Yes, yes, yes.
Okay, sir.
December 12th. It will be around December 12th. It will be starting. Uh, this time, instead of having a late penalty, we are planning to have a broader duration, but we are going to have a early submission bonus. So if you submit early, you will get a certain bonus of the total score. So that is also.
Sir, but sir, could you please repeat?
Sorry.
Sir, could you please repeat?
Yeah, yeah. So last time we had a late submission penalty in the NPP, right? This time we are planning to have a broader deadline with the early submission bonus rather than a late penalty.
Okay, sir.
Okay.
This time also this Trackio part is expected.
Yes.
Sir, could you
So the
please?
detail, so the exact details of the scoring and problem statement will be shared later during the thing. What are the so this exercise will be little different and the marking scheme will be also little different. So we'll put it out in the announcement when the problem statement is finished. Regarding the dates, it is this ones. Okay.
Okay, and final grading, how the NPP scores will be calculated? It is average of two or max of two like that.
So there that is in the grading document. I think there is 1.5
Both are
weightage for
different.
each of the entity. No? Okay.
15 marks for both the NPPs.
Okay,
Yes, yes.
weightage for both the NPPs.
Yeah. Okay.
Sir, could you please do a workflow of MPP, how we can go with that in video?
Um, Overflow of NPP in the sense.
Sir, how we can start with that?
I think in a previous session I shared a notebook, right? So a starter notebook like that, simple linear model was saying. So
Yes,
did
sir,
you?
yes, sir. So the
Uh,
thing is that like how you added that tokens, like all these things and
in Kaggle,
spaces also.
the Kaggle details, the hugging face and those things. You are talking about that.
Actually, sir, I think the problem is you explained last time, but it was not that detailed. That's why it's not clear to many students, including the track IO part. Because I think for you, track IO, you already had that ID created. So people were facing problems
Hugging
while
Face ID.
starting from the scratch.
So you are talking about creating the tokens in Hugging Face, is it?
Yes, sir,
Definitely.
including that part also.
Wait a minute.
Sir, in Trackio, we have to actually add that secret, right? I mean,
Yes,
luckily,
yes.
one of the students, basically, I was struggling for one day, and then luckily someone suggested it. So that's how only I got Trackio marks. So I went through your video a few times, but what happens is like because you know that time is ticking away. Um, I mean, it just adds up. So um, I think a clear demonstration certainly helps. So I think I was
Okay,
lucky that I got that solution. Otherwise, I would not have got those marks.
okay. So let me do that. So, okay, so I'll try to keep it simple yet detailed. Let me know if you have any doubts while I'm demonstrating this. Okay, I'll try to do that. Sharing my screen. The screen is visible, right?
Yes, sir.
Okay. So in Hugging Face, you have to create tokens, right? So you go to your access tokens and this page will open up. And here you can create a new token, right? So I'll create a new token. You can have a write token,
Sir, your
simple write
screen is
token.
stuck.
Again, I have browser settings.
Sir, while you do this, sir, what is the plan for today's call for rest of the hour?
Uh, I was going to discuss week 9.
All right, all right. I'll wait, sir. Yeah.
Sir,
Sir,
Okay,
are
sorry,
you
sorry.
on mute?
Yeah, yeah, I was in mute, sorry. Yeah, so what I was saying is we should take this token, write token from here, uh, go to this notebook, add that notebook. You saw that, right? What I did? Is
Yes,
that
sir.
part?
yes, sir.
Yes. So after adding the secret, we can add the secret to the notebook by copying this code. So this code basically gets the secret, right? So here is the secret value. So to access this to make this available to the Hugging Face Trackio, we have to uh, add it to the not sorry add it to the environment variables. So that we use import os dot environ and here place in Hatcher token. This particular environment variable called capital Hatcher underscore token should be set to this particular value that we have. Right? So this is the initial step for the login credential and all. Then we'll run this. And by that time, we'll also we have to also install Trackio. So this will install Trackio. Then I think I shared some one more link on Trackio docs. Yes. So here we have the required things, right? Yes. So the initialization bar, this one we can take it. We have to initialize a project. So this project name is under that. We have to set the space ID if you want this data to be uploaded in Trackio. Space ID is equal to let me go here. Yes, it should be in this format. So username slash space ID. So I'll put that. Okay. This is the project and this is the name. Just keep the default values. So this is how you unit the run. So after initialization, we log values. I'm going to log some random values. Some random values into the log, right? And after that, I'll be finishing this log. That's it. So now, once the space ID is clear, so it should create the thing. Group is optional. If you have multiple runs in a group, we'll do the groups, but you can have that. Project is the whole container inside the space. So one space can have multiple projects, and the projects can have multiple groups and runs. Runs are the lowest level of things, which will be one line. So first maybe I can also do some multiple runs. I can try that. If you want me to have multiple runs, I'll do this like uh, some 5 runs I'll have. I'll also group this in a thing called test runs. So now this will create 5 runs, and for each run we have to finish this. So this is like I am doing 5 experiments or training 5 models like that. So this is the thing for one model, one experiment with one set of hyperparameters, one training uh, execution. After one training is complete, this is to emulate. I am doing some 5 combinations of hyperparameters, and I am doing 5 runs in that. So after every run, I'll finish this. So yeah, so that I can see that 5 things there. It's import track
Sir,
table. Yes,
the second line that you added, from where we can add,
this
so
one
that tracker dot init.
init.
Yes, sir.
This you can look into the quick start itself. So init will have basically a few things. So if you are using hyperparameters and all, you can also add the hyperparameters that you used here like that. So that will add some more metadata to each run, which hyperparameters you use, you can add to the config for different hyperparameters. Other than that, to identify, you need a project, a run name. Run name and project are very good things to go with. So that those are the mandatory things, project and run name. For spaces, we need to also add space ID. Group name is optional. Configuration you can add if you are trying out different hyperparameters to know that which hyperparameter is being used and all, right? So that config also you can add in this part. Mandatory ones are the project, run name, and the space ID. These three are mandatory for us. Okay. So after
Okay,
this,
sir.
let me run. I'm running this. Now it is first the space doesn't exist, so it's creating the space. So if you have properly included this token, you shouldn't see any login issues here. Okay. It will also show some here for this. It's random. Okay. After each run, it will upload its logs. So if you don't call finish, the data won't be uploaded to the space. Only when you call finish, the data will be uploaded to the space. Okay. I think I haven't turned on internet, I guess. It's on. Okay. Take too long. The last error might have caused something. I guess. Rename this. I think something messed up due to the error. I guess the space. We are just delete this space and create a new one. Okay. This delete that. Yeah. Now the project is there, data set is there, space is there. Yeah. Okay. Mm. Mm. Okay. Yes, been speaking error. Mm. There was some issue with the latest Trackio version. It seems. So they have updated the radio version in this patch. That might have caused some issues. A recent patch that has caused some issue. Okay, now everything is fine. Yes, yes. Now we have the app, and these are the random values that were logged. These two things we logged, right?
Sir, how
You
did you
can see
fix
the
the
runs.
error? Can you please show?
No, the thing is, I fixed the version. So this Trackio is a very recent new library, right? So they have seem to have updated the patch with 2 days before, making it version 10.0, where they have updated the Gradio version, which has caused the issues, I guess. So when I fall back to this 9.1, the previous version, then it worked, right? So this is some bug that they have in this latest version that they have to fix. So until that, we should fall back to this particular version. This will be fine. Okay. This was a very recent one. This was released 2 days ago. This has caused some issues. Okay. So now things are fine. So you will have this data set logged in this particular data set. You can also see the link that is here. This data set will have these things. So this is currently private. We should make this public when you are submitting. So we will make it public by make public. Now this data set will be public. This data set will have the timestamps and the logs that you have for all the files.
So we have to make the this public.
Yes, yes. We have to make this public.
Okay, sir.
Then only we will be able to get the Trackio logs from the API, right? Otherwise, we won't be able to see it. Only you will be able to get the data. So you can verify whether it is made public by opening a private tab and checking whether it is coming there. If it is coming there, anyone can view it.
Okay, sir.
Okay. So that is the thing. So for now, make sure to fall back to version 0.9.1 because version 10 seems to be having some issues with the Gradio update. They have updated the Gradio version that is running the space. So the space is built upon radio, right? The space that you see, this interface is built upon top of radio. They seem to have some fixes with that, which had made this issues. Okay, so now everything
Okay,
is
sir.
fine, right? Any doubts so far?
No, sir.
Is that clear? Okay, okay. Then we'll move on to week 9. Okay. So here we'll have having these five concepts, mostly transformers, and also a hint of what word embedding is. Right. So previously, the techniques that you have seen to encode the words to things are this one-hot encoding type of encodings, which converts a word to a vector. But those vectors are not representing the word semantically in the sense that synonyms are not captured, right? Each synonyms is a unique word in those kind of embedding. But if you are again encoding two similar words in a vector, we want that two vectors of similar meaning to be close in that vector space, right? And also that gives you some semantic understanding of this. And also this embedding should encode the relationship between words also. That is one property that we will be seeing in this word embeddings, right? So understanding relation between two words like that. Right. So this is a famous example that we have. This,
Sir,
uh, yes,
sir, I want to know where can we practice problems on this attention mechanism, all this transformers and all, apart from this practice and
pra-
graded assignments.
practice problems in the sense like mathematical problems.
Yeah, mathematical problems or anything of that sort, or like not completely code or not completely mathematical, or like what we are being given in the course structure in the practice assignment, similar to that kind of problems. Where can we find that to
Actually, sir,
Okay,
more
I
questions to practice.
yeah.
more questions to practice. I think we only should provide. Might not be
Because
readily
in
available in
quiz
this
two,
format.
I mean, I found it difficult because some of the questions I found that whatever we practiced from GA and PS were not sufficient.
Yes,
So
sir. And
Okay. Yeah. So okay, the basic idea is to in these cases, the basic idea is to understand the architecture and also the how things happen, right? So if you have the basic understanding of everything in very detail, you will be able to do things. Also, solving problems helps you like revise those understandings. So I can understand that.
Yes, sir.
Uh, Maybe for n term, we'll try to provide a mock so that you can have some practice questions in that.
Like,
Okay.
no, sir, like, is there any book like the thing where there are
No, no, no.
problems?
Because there is no very standard book on these subjects, right? Because
Yes, yeah, I
these
understand that.
concepts itself are very yearly to be found in a very standard textbooks.
Okay.
Okay. You see, this attention mechanism itself was found like discovered in 2017, which is almost 8 years. Uh, you don't have a very standard book on this case, right?
Yes, sir.
So to give us a standard book with practice problem and all, it would take around 20 to 30 years after that concept being there in the literature.
Okay, okay,
So
okay.
those kind of things might not be available really.
Like I wanted to like see like a problem specifically for attention mechanism only because the problems there are little difficult to grasp the concepts. So I need little more practice to understand it more in depth.
Okay,
Yeah.
so
Uh,
basic things what we can do for now is to understand the formula and the intuition behind it and try
yes,
to understand the parameters. So you can do one thing, try to learn like estimate the parameters. So parameter estimation kind of gives you the exact understanding about the architecture of each architecture, right? What are the learnable parameters and what are the non-learnable parameters? The best way to do that is actually building it yourself in PyTorch and seeing it practically, verifying your results. That could give you some understanding about the architecture in general, right?
Yes,
What
thank
is the
you.
input shape that is going in, what is coming out? Can you predict that? So that's how you can estimate for now.
Okay, so yes, so like got it. Like if you have a basic understanding of the parameters required to train and all, we'll have a
Yeah.
very good understanding.
Yes. Yes.
But sir,
Oh,
still questions will help, sir, if you can.
Yeah. Yeah. We'll try to provide questions for the interim as mark so that we can do that. Okay.
yes, thank you, sir.
Yeah. So this is one good example, like very common example that we see in the word embedding aspect, right? So this is embedding not only the synonyms but also relationship between the vectors, right? So this axis, you can see there will be multidimensional vector, right? So one axis can represent uh, the change of royaltiness, and one axis can represent the change of gender between multiple things, right? So this word in this axis, when you interpolate in that direction, you will get this one. The same thing, if you interpolate this vector in this side, you will get this one. So this is something similar to vector addition. The relationships are encoded with vector additions or vector arithmetic, right? So this kind of things, if the embedding space can represent, it would make more sense. So also it could learn things about properties about unseen data. So if it learns the relationship between a model and sees a relationship between man and king, and it sees a relationship between man and woman, then it could kind of infer what is the relationship between the man and queen, right? Through vector addition. So that is uh, what is the main thing that we are looking for in a good word embeddings. A good word embedding should be able to represent this kind of things. So after training these word embeddings, people evaluated this using this kind of cosine similarity between the vectors and the relationships between different words to get this. Okay. So now how we can get these embeddings? There are multiple ways. So these are the very common ways that early ways methods in which people got these word embeddings. Word to vec. This is the very first thing that actually introduced word embeddings of that sort. And then Glove improved upon it. It's kind of uh, an improvement over word to vec. And fast text is something more uh, advanced than that, which was released by Facebook. So they released this embedding method, and also, and at that time, this was kind of very, when this was released, this was the state of the art at that point of time. After this, the next breakthrough was the uh, this transformer models, and there came this base models, the transformer based models. These provided something called as contextual embeddings, right? So these models that we saw, the basic models that didn't provide contextual embeddings, uh, this provides word-based embeddings. So each word has an embedding. It doesn't change the word embedding depending upon the sentence. This is one example. If the bird, so in these approaches, the bank would have a fixed embedding, and this bank and this bank don't have a different embedding in this case. So this made it clear that these embeddings are not very sufficient to generalize this. So that's when when this attention mechanism came in, people move towards this transformer-based contextual embeddings, which also took into consideration of the context in which the word is present. So each word is encoded, the embedding is created based upon the context. So that is the difference that these models introduced. Okay. So yeah, right. So this is the common mechanisms that are used to train this learning approaches, right? So the word to vector algorithm is kind of trained in a different this kind of manner only. So basically, there are different methods in which that word to vector model can train. So there is this continuous bag of words mechanism, skip gram mechanism. So basically, it's like word prediction. So you give a context and also predicts the next word or the between word, the in between middle word in a certain context window. You ask it to predict and train the neural network like that. And that last layer will act as the embedding for you. So it will be like that, right? So this is the basic mechanism in which you can learn this word embeddings, which is actually used in this basic word to vec models like skip gram and continuous bag of words. Right? And so that's it. Then we look into how this uh, attention module and attention mechanism came into picture. So these are the foundations for the modern NLP. These things are the foundations for the modern NLP systems. All the transformer-based models rely upon this attention mechanism. Okay. So let's see what attention does and how it is helpful. So we also saw that in this encoder-decoder architecture with the RNN, the final state uh, cannot have all the information because of the size limitation in the context vector. That is one thing. So some information might be lost. This context vector cannot hold long sentences, and also training this is uh, very hard. So the single vector bottleneck is what we are saying, right? Because this is a fixed size. So it cannot always store a very long arbitrary information into that context. Some information might be lost when the sequences are long. And we also saw these problems. So that is fine. So these also there, but for very extremely long sequences, this also still suffers. So because of this bottleneck and all. Okay. And then how do
Sir,
we? Yes,
sir, this context vector, right? How it is
yes.
created and how it is decided about the length of that context vector?
So context vector is a fixed length vector, right? So this usually has the dimension of the hidden size of the RNN, or this output, the hidden size will be there, right? For this RNN, that will be the dimension of this context vector. So what we are trying to do in an encoder-decoder architecture is encode a sentence into some context that will contain, that will, we are making it to learn the meaning of the sentence. And then in the decoder, we are decoding the meaning into some other language. So this is kind of a machine translation task, right? This English is converted to this French, as you can see. But the problem with using this context vector is of this fixed size. So it cannot hold information from a longer sentences. It can only take in information in a lesser sequence, usually of one sentence or few paragraphs like that, 2 or 3 sentences at max. So otherwise, we have to increase the context length, but increasing the context length or the context vector size will uh, bulge the network. And also, since this is very long, the recursive nature of RNN had more computation, sequential computation involved. So we cannot make use of parallel processing to fasten this. So that is one thing. It is sequential, and also you have a context vector bottleneck. It cannot represent very long sequences without loss of information.
Sir, we could have just used the output hidden state, right? So that anyways like have information about rest of the sequence. So why we
Each
introduce this new
hidden
concept?
state, you are talking about each hidden state.
Sir, output, the last one. So just before context, right? So the last block of encoder. After
So the
that, just
last hidden state is the context. So the last hidden state you get right, that is the context.
okay, okay, got it.
Okay, this is not another step. After this last input, you will get a hidden state, right? That will be, so I think we saw in one of the codes earlier. So usually the hidden state is a recursive, right? So initially we'll denote it with a zero vector here. And after these things, you will get the output of the RNN is the hidden state of the last iteration. right? That is what you get at the output of the RM. In that output is the hidden state. This will be passed as the initial hidden state to the decoder network. That's how the encoder decoder architecture work with ARM, right? Is that clear? Oh, yes. So this is talking about the yeah attention as an enhancement. So instead of a, fixed thing, we uh, added this attention. So what attention does is something that we'll see here. So attention is that about the translation part, right? So when we look at one translating a sentence, we might not look into it sequentially because the word order might change in the other language, right? So in that case, so there must be some relationship between these words, uh, how these words are related to, right? So for example, the sleeping might have some relation to this cat because this is what it is sleeping, and the mat and on would have some relation because it's kind of saying the position of the cat on the mat. So the on could also have some relation between the cat. So that's how the relationship between the words kind of what we are trying to encode with this attention mechanism, right? So this is some example that is given. The cat is sleeping. So to produce the word, we pay attention to the word cat, but also to say this thing. So this word called coil, right? So this would should for translating this one, we should kind of focus on the man. These three words, right? So to predict that, these three words should be uh, paid attention to. So like that. So similarly, that's how we are trying to encode this attention. How these words are related to each other is what we are trying to encode in that, right? So yeah. So let's see it in more detail. Yes. So these are the encoder hidden states. So this is this now what we are trying to do is trying to add attention in this recurrent neural networks, right? So as I said, so here you have the last context, right? You could also have all these hidden layers coming in, right? All the hidden layers, you can take it and then use this attention to create some matrix and pass that to this decoder to get the idea idea about for converting that particular word. So this is one thing that was raised, and yeah, so that's what we are going to do now. Oops. Yes, right. These are the hidden states from the encoder. All the for all the words, you take the each hidden state, and then you have some attention weight. So this attention weights is something that we are going to learn between these words. So if these are the hidden state, this is something that we are going to learn, and this will be passed to the current decoder state to along with this current decoder state, it will give us the output. This is the idea of attention. Right? So not only we can use the last hidden state, we can also pay attention to the other hidden state, right? Okay. So now this mechanism of self-attention comes to picture. So self-attention is that we are trying to learn. So this is the task of decoding this thing, right? So what is self-attention is that, so assume that we are trying to encode the sentence itself. We are not planning on the decoding part. So then now we should learn the relationship between. So this is kind of learning relation. This is something called as cross attention. This is the input sequence with the output states. So that is something called as cross attention. Self attention is something that we pay attention to this into this itself. So that will be not this input into outputs. This will be self attention will be inputs into inputs itself. How the input words are related. So this is something called as cross attention, which is we are kind of seeing how the input or states are related to the output states, the decoder states. So now we are going to think about the self attention. So self attention has these three components: query, key value, and pair. So query gives the context or the sentence, and key value will give you some idea about what this query means in this particular context. That is something like that. Right? Now let's move into the mathematical part of it. So this is how we have the attention defined. Okay. So this is coming from the idea of attention pooling, like some query key value pair and all. Let's say, yeah,
Sir, sir,
yes.
sir, if we have Q, K, and V, can we calculate the number of parameters? That's what it is.
QKV are the parameters.
No, no. If we
So
have a
here, yeah.
if we have Q, K, and V, like some matrices, that means only they are the parameters, right?
Yes. These are the parameters. See, these are the length projections of the original word embedding. These are what we are going to learn.
So original word embeddings, what that it means?
Original
Okay,
word embeddings mean
like if we have something like a static word embedding that
yes,
will be
yes,
changed to this dynamic word embedding, that's Q.
yes.
Okay, so how will that n by one some n by one static word change to a k cross k1 cross k2 in q or something, a two-dimensional thing? How will that one dimensional go to two-dimensional?
Okay,
Hello?
so this not we are talking about a single word in here. So the query represents the uh, so query is a vector, right? This vector chooses from the whole sentence. So you can consider the whole sentence. So now for the first thing, so query corresponds to which word we are should pay attention to this thing, right? So now we are having the whole sentence, not just a single word. Single word is a vector, but the whole sentence is a matrix, right?
Yes, sir.
Self attention works with this matrix. Sorry. Uh, yeah, kind of works with this whole sentence at a time, right? So this
Okay.
query is something that is learning which word to pay attention to, kind of selecting the word from the sentence. So if we are paying attention to the first word, the weight for the first word in this vector, query is a vector, will be high, right? So
Okay.
query key will produce a value, kind of like that. For example, this will see the query word. This will pay attention to like this. This weights will weigh the words which we are going to pay attention to, and key is the uh, the this query about the sorry is what we are looking into what we are trying to look into this query. What about the query? So this particular word, this kind of transforms the aspect of what we are trying to transform, and this is the relationship between that. So these things we are trying to learn with that, right? So this
Sir,
word in this particular context kind of trying to uh, give the meaning of this is something that these three are related in this manner, right? So if you see this mathematical formulation, so how it is this query and key and value pair is there, right? So key value pair you have query and this key is multiplied in this cross fraction. For example, uh, what you can say, this will be multiplied in a cross fashion. If you see
So,
all possible I for this from Q will be multiplied with all possible K from
so
this one
what is
to produce a
K1
square
and
matrix.
V1 here?
Sorry,
What is
the
K1
key
and
value
V1?
pair. That,
No, like
so
if there is
no,
a
this
sentence.
the okay, yeah, yeah. What I'm saying, this one doesn't kind of uh, okay, let's go. Okay. So sorry, what is the question?
What is K1 and V1 and Q here? If there is a sentence, what is K1, V1, Q? Hello?
Okay, okay. So, yes, K1 and these things are kind of learned projections, right? This doesn't relate to the sentence itself. So this is these are the learned parameters, not the sentence that we are giving as input.
Okay, like initially we have to
These
initialize that with
these are
something.
yeah, we will randomly initialize them like any other parameters.
Okay,
These are parameters of this model, right?
okay,
This doesn't have anything to do with the words. So
okay,
these meanings are what we are believing it will learn.
okay,
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 who should I pay attention to? We are according to the model, we are believing it that this would learn this part, this aspect.
okay.
Okay,
Yes, sir.
Sir,
so attention
how
based.
will this be learned, sir? How will loss be there? How loss calculation will happen?
Sir, can an example be given like for that?
Okay, okay. Loss calculate. Yeah, yeah. What I am saying. Yes, yes. Let's see. So the loss will be learned based upon the task, the word prediction task, missing mask. So, okay, in pre-training process, any model would be having in this transformer-based model, there were different pre-training methods. So in this pre-training methods, the most important one is the mask language modeling task. So how this mask language modeling task work in this is what is used in BERT and other uh, transformer-based model. So in general, we will be using this missing word prediction task to train these models to learn this representation, right? So mass language modeling is like you have a sentence, you randomly remove some percentage of the words from it and try to predict that, like just like missing value prediction task. So these won't be these values will be learned by using that self-supervised missing value prediction task. So for missing value prediction task, don't need a label data set. All you need is a corpus, right? So we do that in a large scale text corpus to learn this ways. So the pre-trained BERT models, like these transformer model, usually are available in pre-trained methods, right? There are different variants of BERT also. Each of them will differ in mostly the pre-training task which is used. So there
Sir,
are different pre-training tasks. Yes.
sir, so the let's say masked data is input and sorry, masked data is like you're trying to predict, so that is like output, uh,
Ah,
and you know the original label. So this is all happening in encoder only.
yes, yes. This will happen in encoder. Decoder also it can happen. It's not like encoder it should happen. So BERT is encoder only architecture. This task can be used in decoder based models also. So the task is something that you can use to learn this representation. Even this, there is not only this particular task. So for the example, the actual BERT model has two tasks that it was pre-trained on. One is the uh, this missing word prediction, and second one is the next sentence entailment. For example, given two sentences, is the second sentence is the reason for the first sentence related to the first sentence, something like that. So that uh, next sentence prediction task is given. So these kind of tasks can be given to learn this parameters, the attention parameters. That's how we pre-train this large language models with attentions, the transformer models. If any models, you will pre-train in something similar to that. RMMs and other case was mainly used to for this downscale task. So we train it on that particular task itself. So when this attention mechanism and the self-attention concepts came in, we tried to learn word embeddings rather than using it for a particular task. And to learn word embeddings, we use this self-supervised training methods like uh, this MLM, which is mass language modeling. So actually, you can see these different tasks in Hugging Face itself.
Sir, in encoder, I can still visualize that you have a sentence and you have QKV vectors and you are trying to predict a masked word, but I'm not able to visualize the same way for decoder.
Okay, do not directly predict the word, right? Before that, you predict this QKV will first produce, and also you won't have a single attention module in the whole network. You will have multiple attention module, which is trying to learn internal representations of it, not the direct representation in one go, right?
Okay,
That is something you have to understand. These explanations in English are just to give you an idea about in general idea, not the actual thing that it is actually learning. This might be some internal representation of these meanings, is what we are trying to say in
sir,
general
that
attention
that I
mechanism.
can so okay. Let's say you have uh,
So this
multiple
value, this
QKV.
what these things.
Yeah.
Okay. After this attention layer, you will get some output, right? That does not get you the what you say the final words. It will be some internal representation. We'll be using some other words to get the final result out of it, right? So this actually trying to learn some internal representation only. We are trying to project the static word embeddings into some dynamic word embeddings, right? Some embeddings only. We are trying to give a final layer of embeddings. For downstream tasks, like masked language modeling is also one task, right? We add a masked language modeling head on top of that embeddings to predict the next word in an encoder model. But in a decoder model, instead of the final layer at the final prediction layer at the encoder level, this last embedding is there, right? We pass it to the decoder architecture. I think in that attention is all you need paper, you have a diagram related to that. It's a very famous diagram that you have. Yes. See this one. So this is the input, and this is the input encode embedding. You have attention, multiple attentions over there. So this will produce an embedding layer, a dynamic embedding. This what output will be not words, right? So if you are training a encoder model, after this embeddings, you will attach a word prediction head that will predict the missing words, right? Some additional layers. But when you are using a decoder architecture, you use this encoder into that to predict the decoder architecture. Okay, this embeddings will go into the uh, decoder architecture to produce the final words. Did you get
So
that part?
what I'm trying to understand, sir, is that for training of decoder QKVs, does it also is the entire encoder and decoder everything is used while training a decoder QKV? So
Okay,
or they are
so
trained separately or how they are trained?
architecture, so you can have encoder models. So BERT is a fully encoder model. This part won't be there in BERT. While as GPT-2 has a encoder and a decoder block. So this is model architecture that we are talking about. What this model can do, right? So if the task will be same, predict the missing words. You can have that as the task. How you predict that differs in both cases. In an encoder only model, a direct one layer will be there, a single layer. You need not predict each word auto-regressively, but in a decoder model, you can have auto-regressive predictions. You predict the first word and then put that into here and predict the next word. That also can go on. But in this one, you can have a single layer to predict the next word, something like that.
So like why can't we have like a bird kind of understanding of each and every word and GPT kind of generation like, like like-
So basically, GPT has that thing. So the architecture of the GPT has the encoder part and the decoder part.
okay, like it has the functionalities of bird too.
Functionality is the architectural similarity, you can call it like that. So
Okay,
there are different architectures, right? So when you look into these different architecture, GPT, T5 model is there, which is a decoder model, and the other uh, subsequent models that were created, right? So the BERT is kind of a family of model. BERT, based upon this encoder models, there were very many family of models called Robert, this Albert model. This kind of different models came in, which actually changes this pre-training task. So there are different pre-training tasks that were introduced to learn efficient word embeddings. So it's not like we use only masked language modeling to train this. So there were different things that were introduced, and also the architecture. So it's not like there is one this nx that is representing that there is like n stacked attention blocks are there. So one attention block and there is another attention block and another attention block is there. Not only one attention block. These are the hyper parameters. This comes under the hyper parameters of a transformer model. Number of layers or the number of attention modules stacked together and the size of hidden size. So each hidden size, this will also have a hidden size, which also comes under the parameter, hyperparameter of the thing. So BERT also has its variants, BERT base, BERT large, BERT medium, this like that. So this will differ in the hyperparameters like the number of layers and the hidden size, right? You have BERT
Yeah.
base, BERT
So
large,
these
like that.
architectures will be taught in detail in uh,
So we haven't gone to that part yet. So still we are, so now what we are looking at is that this one part, so this multi-head attention is there, right? Inside this multi-head attention, there are multiple single head attention. And inside that single head attention is where we are currently now. Okay, this attention is just one layer of the whole network. It's not the whole network.
sir.
It's
So
kind of
this
something similar
QK
to a
and
CNN
V.
block.
Okay,
So just like the CNN parameters are there, right? This UK and V corresponds to one set of parameters in one attention module.
sir. So this QK and V are the only parameters for this attention mechanism, and if like like if there are some uh, uh, vocabulary or context length changes, will that affect the parameters?
Yeah, so assume now we are not going to be directly using this QKV on the words, right? You will be using
Okay.
this on the static embeddings that think something like that. For example, if you are using attention with the RMM, the hidden state will be the input to this attention module. Okay. So
Okay.
this corresponds to the size of this. This also has its own. The QK uh, should have this dimension of this hidden state, and V can be of a different dimension, which the resulting dimension will be there. Something like that. So the QKV, sorry, the QKV has to be in one dimension based upon the uh, so Q and K, so the KV dimension, you will get the resulting dimension in a different thing that you can set up how you want to set up. So this Q is something like an input size and the KV has the size of the output. That is something that you can think of.
Okay.
Okay.
So if the context length changes, the parameters won't change, something like that.
Context length by me is okay. What are you referring to as context length?
Context length, like the
No, no,
input
no. Now
sequence.
don't go about go okay, don't go about the sentence or the input words at all. Just assume there is a hidden state, an n-dimensional vector. So don't assume that. Mathematically, there is an n-dimensional vector as input, and we perform attention on that, and you get some m-dimensional output,
Okay, okay,
right?
okay,
So that is how it will go. So there is Q is some n-dimensional and this KB has some m-dimensional vectors. After performing this attention, you will get something like a n-dimensional vector
okay.
with
So
length.
an
Uh,
n-dimensional vector, where all should I put more attention? That will be given as another n-dimensional vector.
Something like that. Yes.
Okay, fine. Dimensional means
Right.
n by 1.
Uh, what n by one?
N cross 1. N cross 1 and another n
Ah,
cross.
yeah, something like that. No, these are
Oh,
the weights. These are the weights, right? Okay. These are vectors.
okay.
Okay.
Yeah, yeah.
Okay. Yeah. So yes.
Levin, I have some questions on this
Yeah.
QKV.
Yes.
You can go to that expression where it says V is myself, and then how much I am projecting for that attention mechanism, right? There are,
Mm,
because
this
this
one, right?
discussion came up during the TA session also with Fulkit, because the very intent for this is to understand the context, right? So that the embedding, the relationship between the words are vectorized, so that I can
Yeah.
keep them together or I keep them apart.
Yeah.
The relationship
Let
between the
me also.
words.
Yes. Yes.
So should this need three things to decide? Three, because here we have something called a Q, something called a V, something called K.
Yes. Yes. I think I'll
So this is what
understand.
this intuition. Why three things are necessary? Because in a grammar it is not like that. One word will help us to understand the context of the other one, like word, a noun, verb. We have the grammar, right? Grammar is like that. So here, why we should, we are okay. At least okay, three is required because we are doing something mathematically and something happens and learning happens. Why three? Why not two? Why not four? Why not one? How the three has happened? Is there a history? This is what maybe they started with one did not learn, and it has some problem it created. Okay, went to two or three, something like that. Same how we did this convolution, right? Convolution neural network. They slowly improved from 2012. What happened? There was a history for CNN, and then all this current Google Net, ResNet, and all how it has left. Okay.
Yeah, hello, am I audible?
Yes, you are.
Yes, yes. Let me share my screen. Yeah, yeah. I think Karthikeyan was asking, right?
Yeah. Uh,
Yeah,
is there a history of having three? Why we should have three
yeah.
vectors?
Okay, okay. So this, I
Because
think
there is,
this
I
is
see
the,
somewhere, I see my value, I see what value I should show it to others. There are two, why these two are necessary. My value is my value,
okay.
it's the same for myself, and then, or it is like a, it behaves like humans. To people, whoever I want, I will, the behavioral changes, right? Same like that.
Yeah. No,
You can
it's
touch
like
upon.
this. Okay. So I think this diagram would give you an idea about what we are going to do, right? So now this is the input
You can
tokens
zoom
or
in a little bit.
yes, yes. Okay.
Thank you.
Assume these can be the tokens or the sequence of tokens or sequence of hidden state, just some vector, assuming, right? Some vector representation, okay, of the input. It can be anything, any hidden state or the inputs or whatever. So now assume we are having an attention module, right? So this key value, this thing, this is like a cross multiplication of these two. This is a vector and this is some query. So for each word, we'll have the keys. So this key set of weights will learn. This keys will learn. Okay. So we have to what we have to learn. So I said we are going to have the relationship between, like kind of we're trying to learn the relationship between the words, right? So this learns how a word. Uh, okay, let's go to that sheet also. This also, I'll try to relate this to that as possible. Okay. Okay. Who should I pay attention to? So this is like the query. So for example, this part, this vectors are trying to learn uh, like which word should I pay attention to? As that is the query, right? So which words should I pay attention to? Should I pay attention to every word when I translating the sentence, or should I pay only to the important words? So that is something this query vectors are trying to learn, right? And what are the key vectors trying to learn? This is what I am. So a meaning, kind of internal meaning of the hidden state. So this hidden state is something, some internal representation of these things. You can think it of like some transformation over the hidden state that we are trying to learn. We might not directly uh, some kind of linear transformation is some you can think it of like that. So the keys are some kind of linear transformation over the it's kind of mapping it as the linear transformation over the words like that. Vector for each word in the sequence saying that this thing.
Here, the query and value makes sense, right? Who should I pay attention to? This is what I have to offer. So somebody is some every word is offering something. Every other word sees what the other word offers and try to see what is its weight and try to pay attention to for framing.
Okay. Now I think I have that answer for. So see this. So this is how we will be doing that, right? So you said this key is sorry query is who we should pay attention to. It is learning that, right? But who we should pay attention to not only kind of uh, infer that things. So without knowing what is it, uh, we might not be able to. predict the attention score of that. So for example, let's say this part. So I should let me try with some example. Mm, so who should I pay attention to, right? So this is kind of learning uh, the positions or the importance of the positions, how the words occur together, something like that. But without knowing who should I pay attention to, and this is what I am, this is what I have to offer. So for example, not pay time properly, uh, able to say that for example, uh, okay, so without knowing what is what, how am I going to uh, say who should I pay attention to, right? So
I think this SQL query is best fits here. Uh,
uh,
in the lecture slides, Sir has explained about that SQL query. We have to look for the uh,
yeah,
each.
so for something like this. So yeah. So for example, yes. So let's say let me try with the SQL query concept. Okay, you have a query to find. mm, Yeah, so find some values with age greater than this part, right? Age greater than something. So query is the whole thing about what we are trying to learn. So the query. So you can say we are kind of encoding this query into some language in some representation. So key is what is what. So for example, in each row or in each word, there might be some what aspect should I so this is kind of uh, saying uh, who should I who should I pay attention to, or who should I pay attention to means for example in a SQL query uh, we this query is saying to select all the things with some particular age value or some weight value, but without knowing the each values of those words. So, for example, some representation which of the words which contain the properties. So you need a record, right? So in that record, all these values will be there. What to look for in that record? What property should I look? So this is saying what property kind of I should look into, and these are the properties. So combining these two things, we are getting this is the property that I want to look into, and this is the information, and this describes the answer for that, the property value for that. This try to sorry, this is this kind of okay. Let's do this here. This produces the attention weights, right? So this gives you which words to pay attention to based upon the meaning of the words and the meta knowledge about what kind of words should I look into. So this doesn't learn the words that you want to look into, but it kind of learn what kind of words, what are the properties that I want to look into, uh, what are the
Should I
association.
take it like this? Maybe a language like English needs this kind because some words, same word will completely have different meaning in a sentence. Say, for example, river bank. One question was there in the GA. River bank and a bank, both are same spelling, same word. But river bank has a different meaning for a bank than a bank which deals with money. Yeah, but some
Yeah, yeah.
languages have some and every word has a unique spelling and a unique meaning. Maybe because of that,
Yeah.
this these two are necessary, because what I am and what I offer.
Yes, yes. So you can think it of like that. For example, the bank will be the token here, assume that. So based upon this bank, you can say this key transforms it into some relationship between what kind of bank it is. You can think it of like that. It learns more information about it based upon that. This encodes the relationship between the words. You can think it of like that. The properties of bank, what kind of bank it is, things like that.
Okay. Same word having different meaning needs this two values. Key and value is
Yeah, yeah.
necessary. Uh, okay, okay. That makes sense at least. Thank you, Lou. Thank you. Thanks for
Okay,
taking time and explaining. Thank you.
okay. So it's kind of not very easily gettable concepts compared to the other things, other models that you have learned so far. Uh, it might kind of confuse you in a little ways when you try to think it off like that. Don't worry about that much. Uh,
So can you
Honestly,
to
explain
see,
this diagram again, like this? Yes, so this diagram.
okay,
Can you please explain this?
right, okay. So assume that this is the final embedding that we are talking about. Okay, this is the dynamic embedding that we talked about of the words. Some kind of uh, final relationship between the input sentence and the final meaning of the whole thing. So now this is the final meaning of the whole sentence as a whole. Okay.
Okay, sir.
So now this is the input, and this one learns. Uh, you see this one. So this is a vector and this is a vector, and we are actually multiplying them both uh, to get to know. So this kind of learns what to choose, something like that. This kind of learns what it is, right? Kind of like that. So key kind of like learns what it is, and this kind of learns what to choose, what to pay attention to, and now you have a final value called attention weights. So this attention weights is coming from this learned from this key and query, right? So this says you pay this much attention to the first word, second word, and third word, like that. So value kind of learns some kind of uh, yeah, what is the actual uh, what you can say. So this kind of we say that this takes you the properties, and based upon the properties, it is describing some weights to pay attention to. So now for the each word, so this value is some learned representation of this each of this word, right? Some representation of this each of the word. So what kind of uh, for which word, how much attention should I pay in this whole sentence? Something like that. Then we do a summation over that. Then we'll get the final thing, right? Final embedding of the whole sentence.
Okay, sir. Got it.
The softmax is for normalizing.
Yeah, you can think it of like that. Attention weights, right? So we want some value between 0 to 1 for each of these things. So this each of this value would be softmaxed so that we get some value between 0 to 1. Kind of paying attention, how much attention should we pay, how much can we forget about these things, kind of like that, right? That to produce the whole sentence embedding, uh, whole sequence embedding, kind of like that. How do we want to weight the each input sequence or the each input or token or the element in that sequence?
Currently, this kind of encoder decoder is used for all the languages or specific languages.
All the languages. So this is not the whole encoder decoder architecture. This is just one layer in that whole
One
network.
layer. Okay. Mm, mm, mm.
Yes. So this attention block will correspond to a
So
single
for the
attention
attention
head.
mechanism, this is the architecture they use for the attention mechanism. We have
Yes,
three.
just like some CNN, and the CNN has some architecture, right? With the kernel and all. Similar to that, the attention module has this kind of architecture. Then we stack up this multiple attention heads parallelly in each layer. So this is one, this you can call as a single head attention, one attention block. And then multi-head attention would be having multiple key value pairs for the same sentences. So that is what we call multi-head attention. And then with multi-head attention, we stack multiple things together to create this kind of layers. We stack this whole thing, a multi-head attention, a feed forward layer, and then you stack a whole thing again on top some near number of times to get some more rich internal representation of the things.
The output embedding size is our wish, no? It does.
Yeah,
How, yeah.
it depends upon what is the hidden size that you are choosing. I think here is some visual walkthrough of the whole formula over here, the attention weight calculation, right? Yes. Yeah, let's go through this. So first, a scoring function, similarity. This usually we be a product kind of thing, and then we do a softmax over there to get some normalized score, and then this weights we can apply to the values to get the final things. So okay, some visual walkthrough is there. Yeah, each word will have some uh, three representation based upon the key value pair. So we multiply this query and key to get this attention weight, and we multiply this with sorry, and we softmax it to get the attention weight. This that, and then we multiply the attention weight with the value to get the. So this basically this attention weight we are doing weighted sum over the values and the attention weights, something like that. So this kind of all the products will give you some kind of weights after softmax, and this softmax thing we will be using to uh, weigh the values of that to get the final representation of that. Right? So there are different functions that you can use. So this is the like some Euclidean function like that. So Gaussian, this Euclidean norm is used. Okay, so different similarity metrics that you can use. So that's the basic idea.
Sir,
So
can we
some kind of
continue on this?
sorry.
Sir, can we continue on this tomorrow?
Uh, okay, so what should we do now?
No, sir,
What?
it's already 1 hour 40 minutes, so that's why I was saying.
Okay, what was this thing?
Yes, sir, because it's a topic which needs some time as well to process and sink in.
Yes. Okay, okay, okay. Then I think we can close this. You might have been. It might have been a lot to take in a single time. Yes.
So,
Okay.
sir, so given the topic is still cloudy, so what should we do? I mean, there is very little resource, and there are very little books on that.
I'll try to post some kind of materials in the some materials to in the course portal if possible. I'll try to collect something with that to get you some understanding of some blog posts or some explanatory visualizations kind of things. That's what all
There
we
are some
can do.
extra problems too, something.
The NPP2
Problem,
is based on yes, please go ahead.
yeah, yes, that's what all I can do. I'll try to provide some resources. Let's see if that makes things easier.
Sir, when you share those resources, can you share something which has more visual so that it's easy to grasp?
Yeah, yeah, I'll try to find some.
Yes, sir. Visual things and problems, and also which weeks will be included in NPP 2.
MPP,
Please,
we are
please
going,
make NPP2 with all these different concepts. One for this, I think, for the words and the language. Another one we studied another one, RNN, right? The,
yes. So
yeah.
this NPP2 will contain RNNs and language modeling. So basically sequential data. You can think it like that.
So two
Like,
separate problems so that we understand when we do that, and then because this one we need to do a problem and then do various to learn how these things work. Then only we'll get a grip, at least
Yeah,
on the
I'll
ideas.
try to design the question in such a way that you will get some understanding upon the RNNs and also uh, the sequential data processing. Some language modeling also will be there, how you can model. So there are different ways in you can design RNN architectures, right? So I'll maybe try to cover that in the NPP too.
So like week 10 is also included, sir. Week 10.
No, no, I think we can take till week 8, till
Okay.
RNN.
Okay. Week 9, all so like a week 9 is also having like little bit of RNN in that
Week
attention, right?
9, attention, I am not planning to include in NPP for now. Maybe some this word embeddings are something that you can actually expect.
Okay,
So
okay, sir.
you can take a look at some sample code on how you can train a skipgram or word to vec model. That will give you an understanding about the static word encoding techniques. Uh, so you can search for those resources first. So you'll get an idea about word embeddings, how these word embeddings are there.
Okay, okay,
And then you can go about this BERT architectures. So this attention mechanism and all.
okay, sir.
Okay. Okay, then thank you everyone. We close the session for today.
Yes,
thank you
sir.
for
In
the
week 8, some simple word embeddings were used, no, without using this word to wake and all.
Those were like the one hot encoder representing. Those we don't call as word embeddings. Usually we call that as